Students, today I introduce you another very important topic from chemical kinetics. That is mechanism of unimolecular reaction or Lindemann mechanism. Lindemann mechanism, the name came because the scientist Lindemann explained satisfactorily how a unimolecular reaction happened. Unimolecular, that doesn't mean that its order is 1, but its molecularity is 1. Here molecularity 1. What is the molecularity? The number of molecules colliding, that is a molecularity. Therefore, could you collide one molecule? No. If there is collision, there should be 2. There is no collision with one species. Therefore, it was a puzzle, a dilemma for the scientists how to explain this reaction. But if you write, suppose you have a reaction like this, A gives P. We have a lot of reaction like this. Isomerization is one kind of reaction. An isomer of a molecule is converted into another molecule. This unimolecular reactions. Organic chemistry, you will learn such a lot of reactions. A particular isomer is converted to another isomer. Okay. Similarly, a single molecule is decomposed. A single molecule is converted to another product. Most famous example is isomerization. How this happened? What is the mechanism of this reaction? This was a dilemma. Lindemann explained this. According to this Lindemann mechanism, he proposed following mechanism. What is the mechanism? 2 A molecules. When 2 A molecules collide, it should be molecularity 2. Okay, but he says 2 A molecule collides and you are getting an A star molecule, A plus A molecule. Okay. He give this K1, this is K minus 1. Right count. Now he said this A star is nothing but energized reactant. What he says, after the collision between 2 A molecules, you got an energized reactant and a normal A molecule. And the reverse arrow sign indicates these products have a tendency to compact the reactants. Okay. Now, he also says this A star, only A star, K2 gives product. See, A and A collide with another A, but only one A is energized. Second A is remain as such. And this A star which formed after the collision may be reverted back to A or converted into products. The product is obtained by only A star. the product depends upon concentration of A star. Therefore, Lindemann says rate is equal to K2 and concentration of A star. Rate is independent of this. Okay? But again, the problem continues. A star is not the reactant we have added. A star is not the reactant we have added. A star is an intermediate species, high energy species. We don't know the exact concentration of A star, particularly whatever amount is converted into products. We don't know how much concentration of A star converted into products. We have no mechanism, no scientific mechanism till now which can exactly determine the concentration of A star formed. Therefore, an approximation, that is steady state approximation was introduced. Lindemann introduced a new method that is called the steady state approximation. Steady state approximation. This approximation, it defined as in a reaction when a high energized intermediate is formed like A star. Okay, like A star. This is our mechanism. I write a mechanism here. A K1 K minus 1 A star plus A. In a reaction when a high energized intermediate is formed, the rate of formation of that intermediate is equal to rate of consumption of that intermediate. This is approximation. Whatever the intermediate is formed, whatever the speed of intermediate is formed, that much speed that is consumed, that is converted into reactants or products. That is, you will not get the intermediate A star in the reaction once reaction is over. Okay, what is the rate of formation of intermediate? Rate of formation of A star. This is the step where A star is formed. Am I correct? That is K1A square. Suppose you take A star is a product. A star is a product. Therefore, rate is directly proportional to concentration of its reactants. Both they are responsible for the formation of A star. Therefore, K1 A star. Rate of consumption or rate of decrease of A star. This backward reaction is one kind of consumption, that is A star into A, and this reaction also, productive formation also, that is K2 A star. Dear student, suppose you imagine the backward reaction. Backward reaction is a change where A star is consumed and A star concentration is decreased. Similarly, A star is converted into products. What is the meaning? Suppose 100 A star is formed. 70 S star is converted into products, 30 S star is converted back to reactant. For simple understanding, both are consumption of A star, therefore I write together. Now steady state approximation says both are equal. Both are equal. Therefore you can write like this. K1 A square is equal to K minus 1 A star A plus K2 A star equal. Now please get the concentration of A star. We want that. Concentration of A star is equal to K1 A square divided by K minus 1A plus K2. I took the A star common here, therefore I got like this. Now what is our rate of reaction? Rate of reaction, the equation was rate of reaction, rate is equal to K2 in A star. You put the A star, this value here. Therefore rate is equal to K1 K2 A square divided by K minus 1A plus K2. That is rate. Now you are comfort. We are in comfort position because our rate expression contain only the terms of concentration of reactant A only. That can be determined. That can be determined. Okay. Now we can have some cases. Case 1. Suppose concentration of A is very high. Very high. Concentration of A is very high. It is very high initial concentration. At the very high initial concentration, or we can say at the beginning of the reaction, because at that time concentration of A will be very high. K1A this still greater than K2. Therefore K1A plus K2 can be equal to K1A. Therefore rate is equal to K1 K2 A square divided by K1A. K1 and K1 cancelled and A cancelled. K2 is equal to K. Now order is 1. Therefore, according to Lindemann mechanism, a unimolecular reaction follows first order when concentration of A is higher or at the beginning of the reaction. At the beginning of the reaction. Please understand this point. This is one of the valuable points for competitive examination. Question is, what is the order of unimolecular reaction when concentration of A is higher or at the beginning of the reaction? What is order? 1. Okay. Now we can go to case 2. Case 2. Case 2. Low concentration of A. Low concentration of A. At that time, K1A is smaller than K2. Therefore, K1A plus K2 almost equal to K2. K2. Okay? We neglected this term. When A is smaller, therefore rate is equal to K1 K2 A square divided by K2. K2 and K2 cancelled. K1 A square order 2. Therefore, a unimolecular reaction follows second order at low concentration of A. In between them, it has an order 1 and 2. Between 1 and 2, we can say fractional order. Okay? Yes. This is Lindemann mechanism. I think this topic is clear. Now I give you one question. That question is misunderstood by many students. Okay. Therefore, you have to learn this question and numerically along with the Lindemann mechanism. Because this question has been observed in many competitive examinations for post-graduation level. Therefore, please careful that. Okay, question is this. Ozone decomposed as 2O3 gives 3O2 gas. Mechanism of the reaction is step 1, O3 equilibrium, O2 plus O. This is a fast step. Step 2, O3 plus O gives 2O2 gas, slow step. What is the rate law expression? Okay, this is a question. Many students apply steady state approximation here. I suggest you, if there is question like this, step 1, step 2, step 1 is fast, step 2 is slow, you don't apply. You can apply the steady state approximation only if you got 2 reactants heats and you got one energized reactants. Understand that? Then only steady state approximation is applicable. Steady state approximation is applicable only when you have an energized reactant is formed in the first step. Okay? Otherwise, you don't follow. Okay. Anyway, we can come to this question. In this question, rate is equal to K into, rate is expressed in terms of slowest step. Suppose it is K. This is K1, K2, this is K3. So, in terms of slowest step, therefore K3 into concentration of O into concentration of N. Okay, this is right, but this is not the correct answer. Because this concentration of O3, okay, that's reactant. But what is this? It's an energized molecule, or something other intermediate species, that is not the part of your reactant. Therefore, you cannot get the concentration of O accurately. Therefore, your rate law expression should remove or should substitute this term with the reactants. That's must. That is a trick. That is the ability you have to keep to solve this question. But how can? Where is this A is formed in the first system? That A is reacted here. Therefore, if you have an equilibrium, constant, what is that? O2 O divided by O3. Now this is equilibrium constant. Therefore, the concentration of O is equal to, we can write here, I think you have noted the question. Okay. Therefore, from the equilibrium, concentration of O is equal to K into concentration of O3 divided by O2. Okay. You apply that here. Therefore, rate is equal to K3 into equilibrium constant into O3. You apply here. Therefore, O3 square divided by O2. Okay. This is actual rate expression. This is a reaction where second order with O3. Okay. Or you can write K3 into K, O3 square into O2 raised to minus 1. Negative order with O2, the overall order of the reaction is 1. So overall order is 1 because plus 2 minus 1. You carefully do this problem. You can see this type of questions in various question paper. Please practice it. If you find any difficulty, contact me. We can together solve it. Okay? Have a nice day.